Here's a nice fluid mechanics question which explores the idea of mass flow rate. And this is something that a first year student who's doing engineering and more specifically fluid mechanics might see in their first year or semester of university. And if you'd like to see anything similar to this in the future, or if you have any suggestions for any topics or specific problems related to maths or physics, let me know in the comments. So let's try to read the question and see what we have to do. So we're dealing with a cylindrical tube that is fitted, it says coaxially, right, onto a hole made in the center of a large disk. So basically what we have is this here is the disk, this here is the cylinder, and they're both fitted into each other. And then we start pouring water into that hole, okay, from the cylindrical tube. And what happens is that as the water is being poured, then the liquid will start flowing radially away from the center, okay? And the question is asking us to find what is the radius of the fluid spreading in the gap as a function of time, okay? Because if you think about it, what happens is the more liquid you pour, the slower it will eventually start to spread, and we can actually understand why that's the case. So it should come to no surprise that as the liquid is moving this way, okay, this is actually a 3D problem because the liquid is flowing radially, so it's coming out in all directions. So if you look at things from above, then what you'll see is that this is the liquid front, basically, and it's advancing at a certain speed that I'm going to call u, maybe. Okay, and this radial speed depends, of course, on this, depends on a few things, including mass flow rate, how far it moved, and so on. So what the question is asking us to do is, what is this as a function of time? Okay, so how does this cylinder, how does the radius of the cylinder evolve with time? Okay, so we're being given a mass flow rate, which is given to us as mu, but to avoid any confusion, I'm going to call this mass flow rate just m dot, okay, which is, I think, a bit more common. And let's try to understand how the fluid flows out of that control volume, okay, out of that space between the disk and the floor. So what we're actually dealing with here is a cylinder which has a height h, like this. So this is the height h, and the fluid is flowing out in all directions. So this way, this way, this way, this way, and so on, okay? And it's flowing through this lateral area of the cylinder that we can actually find quite easily, right? So the area of the lateral surface area of the cylinder is given by the circumference of the circle, which is 2 pi r, multiplied by h, which is the height, okay? So the liquid is coming out everywhere from this, so it's even coming out from here, here, and so on. And the total area used by the liquid that's coming out is 2 pi r times h, okay? So this is what we can write. We have that the mass flow rate, which is, typically given by rho AV, is rho, in our case, for the area we have 2 pi rh, so 2 pi rh, and then multiplied by the velocity, which I'm just going to call u, okay? And of course, this mass flow rate is equal to the mass flow rate of the liquid being poured into this cylinder, okay? And of course, that has to happen because mass continuity is a thing. Or mass conservation is a thing, rather. So how can we actually find an expression for r? Because we can't just separate r from here and say that r is m dot over 2 pi rho h u. Okay, and the reason we can do that, but it's not very helpful. And the reason is because we've got a u in here, which is also a variable. So u also depends on r, and we have to isolate this dependency somehow. So u, this u, is the velocity of the liquid, and the velocity of the liquid is purely along the radius. Okay, so if r is the distance from the center all the way to the liquid front, what we can then say is that u is dr by dt. Okay, so r is how much the liquid moved in a certain amount of time, which means that its first derivative is the velocity. So that's very nice because we can say m dot is rho, and then we have 2 pi r h, and instead of u we have dr by dt. So we can separate the variables. So I'll have r dr on this side, and on the other side I will have, first of all, m dot divided by, and then we have 2 pi rho h, and then dt. Okay, and now we integrate. So we integrate both sides. Okay, m dot over 2 pi rho h is a constant, which is why I can take it outside of the integral. And if I use indefinite integration, then I get r squared over 2 equals m dot over 2 pi rho h multiplied by time plus a constant. Okay, now we have to find what this constant is, and we know that at the initial time, when we start our stopwatch, the liquid hasn't advanced into that cylindrical space underneath the disk, right? So we have essentially r of 0 equals 0, which gives us, and it's easy to realize that c is equal to 0, okay? Which finally gives us that r squared over 2 is just m dot over 2 pi rho h t. Okay, we can cancel all the 2's. And finally, r as a function of time is the square root of the mass flow rate multiplied by time over pi rho h. Okay, and this is what the question was asking. Okay, so we have the radius of that liquid front as a function of time, and everything else is a constant, and everything else was given to us in the question. So we know m dot, we know rho, we know h, and you can even plot this, and you'll see that the radius, of course, depends on, is proportional to the square root of time, essentially. And that's the end of the question.